In the last video, we are given a collection of jobs and we are given only one machine, and we wanted to know what is the maximum number of jobs that can be scheduled on this particular one machine. Now let's say that we have to schedule all these jobs, but you have more or less infinite number of machines, but you don't want to use all the machines, right? So you want to use the minimum number of machines to schedule all the jobs, right? This could be like a classroom activity in an institute. You have scheduled several classrooms. There are several classrooms and there are several classes which starts at different times and ends with different times, and you have been told that all these classes have to be scheduled, right? You have to find what is the minimum number of rooms that are required to schedule these classes so that no two classes will coincide. Another example could be that if you're working for an organization, there are something called meeting rooms. There are several meeting rooms and there are requests for meetings, and meeting typically has a starting time and ending time, and you want to be able to decide, given a request for the meeting, you want to decide which of the meeting rooms should be used to conduct this meeting, and only one meeting can be held in one particular meeting room. So the objective here is to schedule all the meetings but use minimum number of meeting rooms. One of the simpler way to look at is to just to reuse the previous algorithm. I'll give you one meeting room and give him all the going back to the example of the jobs and machines. You're given one machine, and the first question is to ask if I just give you one machine, what is the maximum number of jobs that you can schedule on this machine? We have seen that if you consider the jobs in the first to finish, you'll be able to find the maximum number of jobs that can be scheduled on one machine. So you can assign all these jobs to one machine, and among all the remaining jobs you can try to see what is the minimum number of machines that are required and repeatedly apply this. Unfortunately, this algorithm fails. We will see an example where this particular algorithm fails to use minimum number of machines. Then we will come up with an algorithm which is the first come first serve, right? So you just consider the jobs are in the order in which they come, and assign it to one of the machines if it can be assigned to that machine. But if it cannot be assigned on any of these machines that are existing that you have already opened, then you request for a new machine and assign it to that. This we will show that is optimum in this video. So let's the problem that we are looking at is that same as the before one. We are given n jobs, start time and end time. We want to schedule all the jobs, but we want to use the minimum number of machines that are required to schedule all the jobs. Okay, so one of the solutions as described earlier is to apply the previous algorithm, pick one machine, right? Then apply the previous algorithm and schedule as many jobs that are possible, right? The previous algorithm, we have seen that if you sort the jobs based on the finish times and you are given only one machine, then this algorithm will give you the maximum. Once you decide the maximum number of jobs that needs to be scheduled on the first machine, then you can look at all the other jobs and repeat the process. So this algorithm we are going to show that is not optimum. That means that the number of machines that are required to use this can be smaller than what this greedy algorithm actually gives. Let's look at this particular example. So you have a job A which starts here and ends here. You have a job B which starts here and ends here. We have a job C which starts here and ends here, and we have a job D which starts here and ends here. So if I have to apply the previous algorithm and try to find out what are the jobs that I need to schedule on one machine if you are given, the first job that I'm going to pick is A, because this is the one that is going to finish first. So once I pick A, C is out because there's conflict with that. Then you have B and D, but this algorithm will pick the one which finishes first. The job that finishes first will be the one which is D. So if you pick one machine and ask what is the jobs that I need to pick, we will end up picking A and D. Notice that once you pick A and D in the first job, C and B cannot be there in the second machine. So you have to again, if you repeat this algorithm, The second machine, you will end up putting C there because that's the first one to finish. After that, this conflict with that, you can't pick this. So in the third machine, you will process B. The first machine gets A and B and A and D. Second machine gets the job C, and the third machine gets job B. So the greedy algorithm has ended up using 3 machines. But instead of doing that, then what we can do is that you can schedule A and B in the first machine, right? They don't conflict. You can also schedule in the second machine the job C and D, because you can see that C and D don't conflict, right? So this algorithm uses only 2 machines. In the first machine you get A and B, and the second machine C and D. So the minimum number of machines required to schedule all these 4 jobs is 2, but if you start with the one machine and schedule as many jobs as possible using the first to finish and then repeat this algorithm again and again, you will not get the optimum solution. So what we are going to show now is that let's consider the jobs instead of in the increasing order of the finish times. Let's just flip the question. So we want to sort the jobs in the based on the starting time. This technique did not work in the case of the previous algorithm, right? If there is only one machine, if you follow the first come first serve, it did not work. But what we are going to show is that in this case this will work. So what is the algorithm? We are going to consider the jobs based on the starting time, and in other words, sort the jobs in the increasing order of the starting time. Consider each job, and let's say that the first job goes into the first machine, and at any point of time there is already m machines that are using. When you consider the next job, if this job can be scheduled on one of the machines, then you put it on this machine. You ask for a new machine only when you consider a new job. It cannot be scheduled on any of the machines, because all of them are processing some job which is being processed by, which actually conflict with the jobs that have been considered now, right? So this is basically same as schedule the jobs in the order in which they come. The first job that I'm going to consider is this job, because this is the one which comes first. I'll put it in the first machine. So next job that is going to come is this job A. So this cannot be scheduled along with the first C job which is on the first machine. So I'll request for the second machine now. The first machine gets C and the second machine gets A. Then we'll consider B. The B cannot be scheduled on the second machine, but it can be scheduled on the second machine because it doesn't conflict with A. So I'll put it on the second machine. Then the next job comes is D, which can go into the first machine along with C. So with this example, you can see that this particular algorithm, which considers the jobs in the increasing order of the starting time or in the order in which they come, and keep assigning to machines if it can be assigned to a machine. You request for a new machine only when it cannot be scheduled with any of the machines that are already there, right? So we will show that this is actually optimum. In order to show that this optimum, let's define what is a depth D of a set of jobs. Depth D is defined as the maximum number of jobs that are in conflict at any point of time. You just look at all the given jobs and given a so let's say that these are the jobs that are given to me. At any point of time, I can this is the timeline. At this point of time, there are 3 jobs which are conflicting. At this point of time, there are 2 jobs which are conflicting. At this point of time, there is only 1 job which is conflicting. Over a period of time, you just look at the number of jobs which are conflicting and keep track of the maximum. That's what is called as D. Now it's easy to see that any scheduling algorithm would require at least the number of machines to schedule all the jobs, because if you look at this D, at some point of time there are D jobs which are conflicting. So no 2 of these conflicting jobs can go into the same machine. So all these D jobs should be scheduled in D different machines. So any optimum algorithm would require at least d number of machines to schedule the jobs. So we will show that the greedy algorithm, which considers the jobs in the order in which they come, or in the sorted based on the starting time, this will require only d number of machines. For contradiction, let's assume that the greedy algorithm, which schedules the jobs order in which they come, uses more than d machines. If it uses more than d machines, let t be the time when we ask for the d plus 1th machine, right? The job the greedy algorithm has requested for the d plus 1th machine, because the incoming job now cannot be scheduled on any of the d machines which are already there. But all the jobs which has already been scheduled in the d of these machines have arrived before this, and they have not completed. That's why this particular job under consideration cannot be scheduled along with any of these d machines, right? So this particular job that is under consideration will conflict with all the d jobs which are right now being processed in the d different machines. So at this point of time, the number of conflicts will be d plus 1, right? That's a contradiction to the fact that d is the maximum number of conflicts that are possible at any point of time. So if d is the maximum number of conflicts possible, then this implies that if the moment you request for a d plus 1th machine, so there will be d plus 1 number of conflicting jobs. That is a contradiction, right? So this proves that the greedy algorithm, which considers the jobs in the order in which they come, is optimal. Let's just ask ourselves what is the best way to implement this algorithm, because you can consider the jobs in the order in which they come, but how do I know that the current job that I am considering, can it be scheduled on one of the existing machines, or do I need to ask for the new machines? So in each of these jobs, you'll just look at the latest job which has been assigned to this. If the end time of that is smaller than the starting time of the incoming job, then you know that this can be scheduled on this machine. So we want to know among all these machines, what is the end time of the last job that has been assigned to that. If that number is smaller than the starting time of the incoming job, then that particular job can be scheduled on this machine, right? So now so this can be implemented using a minimum heap. So h of I will be the end time of the last job that has been assigned to the machine I. So once you build the minimum machine, so this will give us the minimum time. If you look at the heap, and if this number happens to be smaller than the starting time of the incoming job, then this particular the incoming job can be scheduled on this, right? So scheduling on this particular machine is essentially you have to change the priority now. H of I will be changed to the end time of the job that you are going to assign to it. So you are going to call the increase key function, right? So if the minimum of the end time itself is greater than the starting time of the incoming job, then all the machines, the end time of the last job that has been assigned to it will be greater than this particular minimum, which is obviously greater than the starting time of the incoming job, right? So if the minimum itself is greater than the starting time of the incoming job, then the jobs that have been assigned to all the machines, all of them will be greater than the minimum, which is greater than the starting time. So all the jobs will conflict with that. That is the case when you have to request for a new machines. When you request for a new machine, you are basically adding a new element into the binary heap, right? If you end up creating a new machine, you will add an element into the heap. So at any point of time, the heap will keep track of the number of machines that are being used right now, and the priority of a machine is the end time of the last job that has been assigned to it. Now when you consider a new job, if the starting time of that is smaller than the minimum, then it conflicts with everything, the jobs that are there in each of these machines. So in that case, you request for a new machine and add an element entry into the heap, and if the minimum element is smaller than the minimum element in the heap is smaller than the starting time of the incoming job, then this particular job can be scheduled on that particular machine. So that will be basically an increase key operation. We are going to assign the priority as the end time of the job which has been assigned to it right now. So when you considering these jobs as and when it comes, and each time when you assign it to a machine, it takes log of n time. Either you increase key or you add an element into the heap. So the entire algorithm can be implemented using a heap in time which is n log n. So in this video we have seen that if you consider the jobs in the order in which they come and assign it to a machine, if it can be assigned, otherwise you open a new machine. This gives the optimum solution, and this is easy to implement using heaps. You can implement this algorithm in n log n. One of the very good things about this is that this can be implemented in an online fashion. So what's an online fashion? So you don't know all the jobs well in advance, and you know about a job only when it comes, right? So this is like a meeting things that happens when you want to conduct a meeting. You just say that I want to conduct a meeting starting now, right? So the algorithm is doesn't know what are all the jobs that are going to come in future. It has to take decision based on what are all the jobs which are already there, right? So if the algorithm is considers the jobs in the order based on the starting time, then you need to know about this job only on its arrival time, right? So another example that you can think of is the downloading some files from the internet, right? So if you click on a button to download, that's the time when the download actually starts. So if there are several processes which has to be used to download different files, then the processors will not know what are all the different files that you want to download when you start using the computer, right? So you will know about the job only when it arrives, right? That is the starting time, and you're not going to store any of these jobs, so you keep assigning to different machines as and when it comes. So this algorithm is can be implemented in online fashion. One other example could be that you're a station master in a railway station. There are several trains coming in. So you know that a train comes in only when it has come. So you have to decide which of the platform it has to use for stopping, and after it comes, you just assign it to any one platform which is free, and so after it leaves, that platform is free for the next time. So even if you don't know exactly the timetable, and you only know when the train arrives, and you only know when the train has left, you know that the platform is free. So the algorithm that we describe says that as long as one of the platforms that you have already used is free, you keep repeatedly using the same platform. But if all the platforms that you have used is busy, then only then use the next platform. So we have seen that this algorithm actually gives us the optimum solution, right? With the previous algorithm, it sorted based on the finish times, right? So cannot be implemented in the online fashion, in the sense that if you have to consider the jobs based on the finish times, then you need to know all the jobs that need to be scheduled in the beginning. So the summary is that the second algorithm, which considers the jobs in the increasing order of the starting time, can be implemented in the online fashion, where you will know about the job only when it arrives. But if you have to use the first algorithm, then you need to know all the jobs well in advance. Only then you will be able to sort it based on their end time. So that is the advantage of the second algorithm that we have considered. In the next video, we will talk about metroids, which gives us a general framework to discuss greedy algorithms, and we will use this technique to show that several greedy algorithms are optimal.